All right, everybody, how we doing today? Doing good. So today is let's see, let me do it. March 30th, 2026. This is the frequency response lab. You know what? I'm gonna add lab 6, okay? Because people were wondering, oh, why did David push this? Why did David do that? Because honestly, frequency response ain't that hard to teach. It's not that bad, okay? I'm gonna make sure you guys know. But then, I'll do a what do you call it? I'll ask you guys some quick questions. Before that, I brought some nice little snacks. I brought some plates. They're the nice. Is it the Dixie plates or whatever? I don't remember. They're gotta have a little, price on a good plate. Okay, don't want them paper plates that break down. So yeah, go ahead, grab some snacks. I told you guys you can have your Starbucks, and if you guys want to go grab another drink right now, be my guest because I am recording this. So don't worry, relax. Okay, I want to make sure you guys have fun. All right. So. First questions are first. You guys know what a Bode plot is? Raise your hand. Right? Okay, that's good. When did you guys learn that? 221? Who'd you guys take it with? Pushkin? Oh, okay, that's great. Wait, what about those who haven't? Who doesn't know what I'm talking about? Bode plot? So everyone knows what a Bode plot is then? Not that hard? Is that good with everybody? But I want to know how they taught it to you, okay? Because honestly, I've heard many different ways. I'm gonna put PTSD. Thevenin circuits. Yeah, I see some shucks. Yeah, because how are they teaching you that? And by they, I know it's your 320 lecture. How are they doing that? Just showing you a piece of paper, saying this is the answer, and not doing it. Is that how it usually is? Yeah, and then they keep throwing it at you, saying, if I keep throwing this problem at them, maybe one day, and I said maybe, they'll get it right or not get it wrong. That's not how we do things. Or maybe some people have a preferred style, so that's why I'm going to do it the way I want to do it. I pulled a lot of you students, and I think a few of you students are a little concerned about the future of your education. So I want to give you guys a taste of what that is. So it's going to be a half lecture. So I'm going to be going over the frequency response lab. I also have this nice thing in front of me. This right here is the, actually, let me show those people at home. This function generator, right? But there's something special about this function generator, and it's the only one, well, there's two of them, that has the enabled arbitrary function generator port, AFG. So for you gentlemen right there who have that special thing, that port's disabled until you pay like the $1,000 or something fee to unlock it. So it's like if Apple gave you like a PC, but you have to like unlock, or I don't know, pay to like unlock it. Or what's that BMW or Mercedes thing where it's like you have the features, but you have to like pay for them or something like that. I don't know for those who drive one, but anyways, why am I going to pay for something I have to pay again? Anyways, so it's going to be an active lab. I think some institutions do this where they teach you and you have fun, and then there's like a homework session where you come in during like office hours or open lab and then finish your homework and come back. So this is a style I want to try to teach you guys. Well, we also have just one of these things. So I'm like, it's going to be a long lab if I were to just pass this to every table and then you have to redo it or something like that. So I thought about it. I'm like, it's going to be painful. So I think this is the better way. Is that good with everybody? Plus, no pre-lab, no post-lab. Just listen, enjoy, okay? And then I'll publish Lab 7 and Lab 8 later, I think today, tomorrow. Gosh, and then I know who's in my 360. Yeah, I'll promise you guys your video. It's uploaded. I think it's uploaded, but I haven't published it fully on Dr. Morris's website or webpage. So I got a lot of things. I'm busy. And then I have a special surprise for everyone in here. After this lecture, I'm going to be recording a separate lecture video, but I'll save that surprise for later. So I'll give an hour for this and then an hour for what I want to talk about, okay? Because it's a very important tool I've been working on for the past, or not a tool, but just an acquisition thing I've been working on for the past 2 weeks. So it's very annoying. But anyways, so you guys know, so what's frequency? Just, I don't know, just like a cycle, right? 1 over seconds, frequency of something happening. Like, oh, I throw this, I don't know, wheels, or I don't know how to explain it, but frequency is just a cycle, okay? That's all it is. Or what's a period? That's just seconds, or how many times something happens, or that rates that it happens, like 1 second, one thing every second, or something like that. Does that make sense with everybody? Is that clear? Okay, I'm trying to start with fundamentals because I'm not so sure what I'm working with right now. So I'm gonna take it very basic. So you guys are used to what's his name? I'm gonna draw this. Okay, this is gonna be familiar to my signals and systems students. Okay, what's his name? Let's see. There's 2 ways if I can teach this, but we have time. I'm gonna put voltage right there, right? And if I put like some type of signal right there, right? And let's just say it's this period. Let me just draw some more stuff. This period right here, okay, is 1 millisecond. Okay, is that cool with everybody? Why'd I choose 1 millisecond? Because it's easy to divide by 1 over itself, right? What's the frequency? Is that cool with everybody? You know why I choose 1 milliamp, 1 kilo ohm, 1 millisecond? It's the easiest number to divide. And then there's the other one, 1 micro, 1 mega, and then there's nano, giga, all those cool terms you guys need to learn. Is that cool? That's how I teach. That's how my mentor, Dr. R. Jacob Baker, he taught me. It's better to teach you easy numbers, to teach you the theory, than it is to just give you what was that weird resistor number you guys got? R4 is equal to 3K ohms on that Thevenin quiz. I don't want to use weird numbers. I want to use nice numbers, okay? Because I want you guys to learn, not being in pain, okay? So there's a special little graph I can draw for you for this, okay? And it's consistent of this. So let's just say I have the voltage right here, and let me just do like 1 volt, right? Does that make sense? Okay. And then if I were to draw this in terms of frequency, okay? Does that make sense? All good? So here's the same volt, right? But if this is 1K, if I were to do this as 1K, right? What should you see in terms of frequency? It's just a little stick or something like that. It's just going to be this right here, okay? 1 volt. Does that make sense with everybody? Not that hard? Right? Easy? Anyways, what if I, what's his name, added another wave, okay? And I'm going to add it like, what's his name? Do I want to add it in here? I don't know if I should, but I'm going to draw something on another page, okay? Because some people are confused about how frequencies react, okay? And that's okay, all right? We're here to learn. So let me see how I want to draw this. If I were to do this, boom, like that, right? Just a squiggly line, right? This is 1 kHz. Is that cool, right? 1 kilohertz, all right? Plus, maybe I should have made this a little bigger. Just drawing like a 10 kHz signal right there, right? And let's just say this is 1 volt right there, right? Is that cool? And then this right here is like, I don't know, 0.1 volt. Does that make sense? A really small little squiggly line, okay? And if I were to add them together, right? How do we add them? A summation circuit. What's a summation circuit? Just 2 resistors that sum to 1 node and mix into 1 node. Do you guys know what a mixing circuit is? An op amp. So you know, like because some people are gonna get confused. Okay, if I were to do 1K, how do I know all this? Good instruction. I don't know. Anyways, if I wanted to do this minus plus, right? Remember the op amp lab, right? This might be a project you want to try and implement. Okay, I'm giving you guys. I'll talk about the final project maybe next week. I'll publish it really soon. Okay, and then this is an op amp, right? And it's got to have negative feedback. Is that correct with everybody? So what I do? Feed it back like this. Is that cool? This is 1K. right? And let's just make it 1K. Is that cool? How to add two different frequencies, add frequencies with a mixing circuit. You have current, okay, someone's not understanding what I'm saying. If I have current going in, so I don't know, like I1, right? Current going in, right? This is V in 1, right? And this is V in 2, correct? What's the voltage over here? If this is ground? 0. Is that cool? Everyone understanding these fundamentals? Everything I teach you in these labs is very important. If you're forgetting what this is, I don't know, talk to me, okay? Or maybe I'm doing something wrong, okay? Anyways, this right here is I1, right? Some current I1, right? I2, right? Would be this branch. Does that make sense? What's I1 equal to? V in 1 minus 0 over 1K. Is that correct with everybody? What's I2 equal to? Same thing, V in 2 minus 0 volts divided by that 1K resistor. Is everyone understanding how to get the current from 2 voltages and a resistor? These are very basic fundamentals. And if I were to give you guys an example of effort, let me see, because this is stuff you guys should know. I shouldn't be reteaching this, but it's okay for demonstration purposes. But I had a student say, a senior tell me this. Hey, David, if you teach 221 or 320, can I just retake it with you? And I'm like, you're not wrong there, but I don't want you burning effort on like the basic things. I want you going into modern tech, into advanced topics, transistor theory or IC mixed signal design, stuff like that. But if your fundamentals aren't there, like, I don't know, stuff like this, like that should be easy to understand, are going to fly right in front of you, okay? So that's why I want to teach 221 or 320, but I'm working on it anyways. So I have currents mixing in, right? What's the current going backwards? Or I don't know, okay, I'll do it like this. F. Is that cool? If it's going from plus to minus, what's that current? V out over, yeah, there you go, you see? And this is called a mixing circuit, okay? It says, what do you call it? It's, shunt mixing, and then you have to sample this, okay? Is that cool with everybody? Funny enough, I'm teaching this to my 420 lab students. I taught them last Thursday. I was like, what is this, okay? Actually, let me show you what I was trying to do. Let me see. Chrome, CMOS Baker book, and I highly recommend you guys get this book, okay? It's pretty chill. I like it. Which one should I pick? Let me see. Hopefully this downloads, okay? I'm not trying to say to pirate things, but you know where to find things, okay? Who's taking 420 next year? Yeah, that's offered next year, so I'm not the lecturer for that. I'm just a lab guy, okay? Where we build chips, okay? So let me just let that download in the background. But anyways, everyone understanding what I'm trying to do here? If I sum these two, what should I get? You think I'm going to get something weird right here? Let me just do something funny, okay? Because I don't want to talk too much about this. If this right here was 1 volt, right? Does that make sense? And this point right here was 0.1 volt, right? What's 1 volt plus 0.1 volt? 1.1 volt, right? So if I were to just draw right there, right? But if I go like to the next hump right here, like it's like minus 0.1 volt, right? So what's 1 volt minus 1 volt? Oh wait, 1 volt plus negative 0.1 volt, 0.9 volts, right? So that means I should get something like, well, right here we're like I don't know, like 0.9 or I don't know 0.95 or something, and this right here is point. Does that make sense? What I'm trying to do, I'm trying to make sure you guys know what it's going to look like, okay? Just picture it, all right? We're adding a small little noise to this signal. I'm going to say it again. I'm adding noise, right? So if I were to add noise to this signal, what's it going to look like? Guys like that answer? Is that cool? So what happens to the frequency response, or if I were to do a fast Fourier transform, and by the way, all these function or oscilloscopes can do FFTs. I don't teach that, but I want to put that into a few of these labs, maybe like my 300 in the future. But anyways, F, right? And V right there, right? What's this plot going to look like if I have 1K and, I don't know, 10K, right? I'm going to get that 1 volt right here, right? Is that cool? And then I'm going to get, I'm just going to write it right there, 0.1 volt. Is that cool? Everyone understanding what's going on? Thank you, thank you. And I'll probably show a little demonstration soon. Anyways, so you guys know that noise is pretty bad, right? And or high frequencies, you want to get rid of them, or we can go the other way around. We want to get rid of DC. Does that make sense? Okay, this is where frequency responses come to play, Bode plots, okay? Because we can build page 2. We can build a filter, okay? If I wanted to get rid of this, right? And then let's just say if I build a filter, I'm just going to build a filter. What's a filter? It's a thing that just filters out what you don't want, or it's a type of filter that filters things that it wants, right? So like think it's like a weird double negative. What's a low pass filter? A filter that passes low signals, right? So what does it reject? High frequencies. What's a high pass filter? Yeah, band pass, band stop, notch filters, Q filter, Butterworth filters. What's a Butterworth filter? It's a special type of filter. You'll learn that in DSP or higher level signal systems classes, okay? But anyways, let's just say I wanted to build a filter to get rid of, let me just do, here's 1K, right? Does that make sense? And then here's that 10K. Is that correct? And I wanted to build a perfect filter that just stops right there. Is that cool with everybody? Right? So we filter out that 10K. Make sense? Anyways, I'm just trying to show you from an electronics and a signal processing point of view what I'm trying to do, okay? And in reality, it's kind of not going to look like this, but I'll show you what I mean, okay, in the next page. What's the easiest filter you guys know? Hint, hint, we already talked about this. Low pass filter, right? Filter. Right? What's the simplest one? RC? Pretty chill, right? What's that look like? Right? It's got a resistor there. It's got a capacitor right there. Does that make sense? R, right? What's this over here? See? Simple stuff like that. Then I got V in as a function of time, and then V out as a function of time. Okay, my signals and systems students are getting scared because they know what I'm going to do next. All right? Does that make sense? What's V out equal to? All right, let's start simple. I'm going to scare people. What's the current? Anybody know? What's the current going through this resistor? V in minus V out over R. Fundamentals, okay? You guys seeing what I'm trying to talk about? Okay, but what's the current in the capacitor? C D V out of T over dt. You guys liking these refreshers? Right? Making you guys confident that your education's still in good hands? All right? So that means if I were to find what the current is, if I wanted to, I'm not going to go deriving this. Is that cool with everybody? And you see that differential and then this normal term? What does that mean? You got auxiliary questions. All right? Which means we're going to have an exponential Euler's equation, all that stuff. You guys, from my signals, Dr. Morris's class, or Dr. Stuber, I don't know if you guys already taken him. Right? I'm not going to do the work for that one because, let's see. Do I want to? I think I'm gonna avoid it because that's the hard, painful way. Okay, but this is where it's coming from. Okay, but we are engineers. We have a special tool. For those in Dr. Morris's class, so you guys are getting double lectures. Okay, this is great. Okay, we have a thing called the Laplace transform. All right, where basically in short terms, okay, we convert all these we convert all the capacitors to like S terms. Okay, does that make sense? Right. So if I were to redraw this, what's the impedance of a capacitor in terms of S? Right. What's the impedance of R in terms of S? Just R. Does that make sense? But what's S equal to? J omega, right? What's J omega equal to? Or what's omega? 2 pi f. And you see how we can relate S and F? What's F? Just a frequency, correct? Remember that 1K, that 10K frequencies, correct? Right? And what's omega? Angular frequency, right? So everything's going to be scaled by 2 pi. Is that making sense? So when you go into your controls class and you start seeing like circuits that are like off by like a factor of 2 pi, they're probably using omega, okay? So if you want to convert it back to the real linear frequency, you just divide by 2 pi, okay? That's very important. That actually tricked me up at my first job because I was like, it's S, right? And they're like, yes, it's S. And then I think my boss was like, oh, we got to convert this to real number. Why is everything off by a factor of 6? Oh, yeah, 2 pi. Okay, don't forget that, all right? LT Spice also does linear frequency, okay? So when you're solving it, you can solve any of these circuits, okay? Just don't forget the 2 pi. That making sense with everybody? So I'm going to redo this again. Should I redo this on a different piece of paper to make it easier? Right? Or no? I'll just redo it here. Plus, minus, right? Plus, minus. All right? And then let's see, how do I want to do this? Everyone knows what an impedance is, right? It's just a variable, correct? Let me see. If I were to make this the impedance of C right there, right? And this right here, you can translate it to the impedance of R, right? Does that make sense? Okay. Let me see. Okay, let me just draw something different. Or some people use X, I use Z. ZR. ZC. Is that cool? Is this a lot cleaner to explain? V in, V out, right? What's a voltage divider? What's V out? V in, right? Times the resistance of this right here, ZC over the total resistances, right? Is that cool? Everyone following? I'm not going too fast, okay? This is technically supposed to be the lab, but I only have one piece of equipment right here, okay? Anyways, plug and chug variables. V in times 1 over... Should I cheat or should I just keep it in terms of S? Cheat, yeah. J 2 pi F, right? Then R plus J, or 1 over J 2 pi F, right? For those in Dr. Morris's class, I taught you guys the cheat code on how to do this easy. Or actually, I think I taught you guys from the first lab. Remember that one trick I taught you guys? If you have, what do you call it? If you treated this as like numerator right here, right? And this is the denominator, right? And you have another numerator here and another denominator right here, right? And although to get rid of like this denominator term, you just multiply everything by d over d, right? Is that making sense? How do I make this clean? Vn times 1 over, what do you call it? J 2 pi FRC plus 1 in terms of F. Boom. Answer to experiment 1 that I wanted to give you guys today. Then what do? Plug and chug, correct? So if I wanted to know what V out is in terms of like, oh, if the frequency was like 1K, right? Or 10K or 1000K, right? You guys see how annoying that might get? You have to like plug and chug numbers, right? So there's this guy, his name is Bode, and he came into like life and said, let there be less headaches, okay? Page 3. So now you know the precursor to what I'm talking about, okay? Because this is what I want people doing. I don't want people struggling. I don't want people having a hard time, okay? Okay, and let's see if I remember. Okay, Bode Plots, there's a few rules you need to know. So one of the easiest rules to learn is there's like these knee frequencies. Let me see, let me show you. They're pretty simple. There's zeros, and then there's poles. Maybe I'll just draw like this. Pole. Yeah, zeros go up. No. I'm gonna mess things up now. Poles. All right. Is that cool with everybody? And this is in terms of F and F. Okay. I'm just gonna draw some stuff, and then this right here is gonna be 20 log or dB, okay? Decibels, you guys know what a decibel is, right? 20 log V out over V in, right? To get total power. Does that make sense? Power. All right. Anyways, so what's a zero? If you guys remember the Laplace transform, it's just I don't know, just a zero right there. Zero. I don't like this marker, right? Or what if I draw another zero right there, right? Zeros. What if I draw a zero right there? It's also a zero, right? Right? Okay, I know my signal system people are like, what the heck did you just do? Or what if I do a zero right there and a zero right here? Z conjugate 1 and Z1, right? Conjugate pairs of zeros. Is that cool? Yes, this exists too. It's pretty cool. What about poles? You can have a stable pole right here, right? Right? Remember from signals and systems? What about this guy? P1 and P1 conjugate, right? Is that cool? What if I put a pole right here? Unstable pole. You guys remember this? Signals and systems? Yeah? This is going to blow up. Just go to infinity. Is that making sense, everybody? So zeros like to make things like go to zero. Okay? Poles like to make things go to infinity. They go up. Okay? So if I were to put a pole, let's just say right here, this is my 1K pole, or 1K zero. Okay? Is that making sense? Or actually, this is the S domain. This is just for demonstration purposes. Let me see. 1K, right? At this point, it should start turning into like a zero, right? And this is 20 log. This is a power, right? So things start going down. Okay? Is that making sense with everybody? So if I were to keep going, let me just get another mark because this thing gets really messy. Okay? This right here is 10K, right? Right? Is that cool? Let's draw this right here. The rule that you need to learn, okay, this is your zero. The rule that you need to learn is that when you draw Bode plots, the slope is going to be, what do you call it? I'll just give you the answer. 20 dB per decade. All right? Is that making sense? Every time you multiply by 10, right? The frequency goes down by 20 dB. So if this was 0 dB right here, right? And if I were to draw a line like this, right? What's that value? Right here. Minus 20 dB. Is everyone understanding what I'm doing? If you're confused, please let me know, okay? Is that making sense? What if I go to, I don't know, 100K? Right? What's that value? Minus 40 dB? At 100K, whatever this zero filter, right? That value is going to be minus 40 dB. Is that making sense? And then how do I convert this back to a voltage? Or linear function. Value is equal to 10, what do you call it? E to the, what do you call it? This is where I'm starting to crack up. Let me see. Minus, no, I think it's, what do you call it? dB over 20? I think that's correct. You tell me if I'm wrong. If it's 0, right? E to the 0, right? Oh, wait. 10E. Maybe I'm doing this wrong. Hold up. Give me a second. I don't want to teach you misinformation. Oh, there's my CMOS book. Bode plot convert to linear. Guys shocked that your lab director sometimes chokes. Okay, there it is. You can look this up too. Think I'm teaching you something wrong? See, where is my function? You guys saw it too, right? Linear, right? I just put an E right there, okay? Is that cool? 10 to the power of your dB, right? Over 20, right? So what's 10 to the power of 0? 1 volt, right? Is that making sense with everybody? So what's 10 to the power of minus 40 over 20? So that's 10 to the power of minus 2, right? What's that equal to? 0.01 millivolt or volts, right? So what's 10 to the minus 1? 0.1, right? 10 to the minus 2, right? 0.01. All right, easy, easy. Anyways, what does that mean with our poles? Let's just say I'm looking at, let me grab another color. You guys like the colors? What color should I use? Purple? Huh? Green or purple? Green? Yeah, I heard a green. I heard someone say, I want to see green. Yeah, look at all these colors. Can you see this? 1K, right? 1K pole. Is that making sense with everybody? Technically it should be here, but if I were to do the following. 1K, right? What happens at the 1K if I have a 1K pole? Just goes up, right? And then here's 10K. And if I keep going this way to 100K, what's the slope? Well, maybe I didn't tell you this, but the slope is also going to be slope. It's going to be 20 plus 20 dB per decade. Is that cool? And then this right here is minus 20, okay? Minus 20 dB. So a 0, you get minus 20 dB per decade, right? And a pole, you get plus 20 dB per decade. Is that correct with everybody? Everyone following? That's the only thing you need to know. It makes our life super easy. And then Bode says, just look at the plot, mix things, okay? So, all right, I'm going to teach more signals and systems, okay? Because that's my major strength. Plus, I think it's cool. Because someone asked, when do we do signals and systems? Like, I want to apply it, but it's all just MATLAB and math, and I don't like them. And you can do it here in the labs, okay? So there's this thing called pole zero cancellation, where here's my Laplace transform, right? And let's just say let's grab a red marker, because I know someone can't see red, which is okay, or green. Was it green or red? I don't remember. It was red. You can't see red. Do you want me to use red? Or what do you think? You don't care? Okay. Weirdly enough, I actually don't have a red. Or maybe I do. Let me see. Yeah, that's crazy. I actually don't have a red. That's funny. I'll use this magenta. Okay. Let's just say I have, let's see, how do I want to say this? I have a pesky pole, like right here. No, I'll just draw it for me, okay? That's a pole right there, right? And poles usually take us to infinity and blow our systems up, right? And we want to get rid of them. How do we get rid of a pole? Actually, let me just draw its conjugate, okay? That's my red. We can use, let's just use baby blue, okay? You can add a 0. Okay? Right? And then adding a 0. So this is a conjugate pair, by the way, okay? This is how you do it, okay? When you add the 0, and if I were to do my Bode plot, I can't spell today, y'all. If I have a 0, right? Let me do my 1K. Right? And it goes down like that, right? Plus pole. Right? Is that making sense? What does this all equal to? Making sense, everybody? That's how you start controlling these graphs. All right? This is a very powerful tool for if you need a quick calculation really fast. I don't want people going back, or if you want to, be my guest for a very accurate value. You can use this, punch this in MATLAB and get your answer. But if you're on the field and you need a quick answer, this Bode plot's probably one of the most powerful tools you can ever use, okay? And it can also do frequency response or phase responses, okay? This right here, all Bode plots right here, these that I'm showing you, these are all magnitude responses, okay? Right? Magnitude responses, how to get rid of, like how to change things in terms of frequencies, right? The value. Is that cool? So let me teach you the other rule. Page 5, okay? So I just said phase responses, but let me just show you how that works. Let me use this black marker, okay? So if I were to show you zeros, okay? For Bode plot, okay? Okay, so this is my frequency, right? And let's just say my Bode plot's right here at 1K, okay? You guys like that I'm using 1K? Right, cool. And then let me just remember, because zeros are great at making sure, let me see, because zeros are on the top, they add a frequency, they add things, they go up to 90 degrees, and then poles are on the bottom, they reduce your frequency, they reduce the frequency. Let me see, let me remember, I'm blanking out right now, let me see. Anyways, I'll just show you what I can do. If this is a 0, right? And if I go to 10K, right? Let me go to 100 ohm, 100 frequency, right? 100 hertz, right? And if I go up like this, right? Everyone understanding what's going on? Everyone can draw me a 0. Is that cool? So, let me see. What's the phase? Maybe I should have shown, let me just look at something for a second. Because sometimes this is my best friend. Pole, negative. 0, positive. So, here's a trick for all Bode plot phase responses. If I were to draw a new, let me just do this. This is a the phase right here in terms of degrees, right? Is that cool? Here's the easiest answer I can give to everybody. Let me see, because this is a 0. No, wait. This is a 0, right? This is not a 0. This is a pole, correct? Someone catch me, okay? You guys like my edit? because the pole goes up, goes to infinity, correct? Someone please catch me, okay? So let me see, going back, because technically this is kind of what I'm doing. No, let me see, because poles, oh wait, am I teaching you things wrong? Hold up, give me a second. I'm blanking out right now. Someone should catch me when I do mistakes. It's okay, don't worry. You guys don't know. I do. How's your guys' weekend? Long, right? You know why it's called a zero? Right? Because it goes down to zero. Right? Is that making sense? Because a zero looks like a zero. Right? Goes down to infinity. Negative infinity. Right? Does that make sense? And then pole. I'm thinking about Laplace transforms, okay? Okay? So if I have this zero right here, and I have this pole right here, right? What's a pole look like? A pole, right? Like that, right? It's supposed to like be a tent. Okay? It's supposed to create a tent. So if I had this following thing, like this, see, this is why I love teaching, because it teaches me again, okay? So if I wanted to draw a pole, so let me see. A pole gives me this. I want to make sure I'm doing this right, okay? Bode plot pole. Did I do this right? Yeah, because poles are supposed to go down, and then zeros are supposed to go up because they increase your free. See, this is why I love. There you go. Oh, come on. If this is a pole, right? The pole is supposed to create a pole. You see, if I were to flip the, you see how it looks like this, right? Or from your angle, it looks like this. And if I were to flip it like this, it kind of looks like a pole, right? Is everyone understanding what I'm saying? Today is one of those days, okay? See how, you see this right here, right? If I were to tilt it like this right here, you see that right there? It's looking like a zero, right? And if I were to do something over here, right? And if I were to tilt it like this, right? And it looks like a pole. Okay? Everyone following me? Page 6. Which means I gotta give you guys your education's worth. So this right here, this is not a zero, this is a pole. Is that making sense with everybody? Is this clear? Because I was looking at this, and personally, you want me to give you the answer to what this is gonna look like? It's supposed to filter, right? This right here, the answer is this. Is that making sense with everybody? I looked at that and then I was like, something's wrong. It's supposed to look like this. This is a pole. Poles are supposed to go down. Okay? Is that making sense with everybody? Because as f goes to infinity, right? What's the value of v out? 0. 1 over infinity is 0. Does that make sense? So it goes down to the negatives. Does that make sense with everybody? And then what happens if you have 1 over 0? Yeah, that's where it starts making the pole, right? Goes to infinity, right? Laplace transforms. Anyways, pole. Do you guys like poor instruction? I don't. Pole. I'm starting to debate what I'm doing right now. Anyways. Everyone understanding what this is? Okay? Let's redo this one more time, okay? Let me see. Let's do a poll. Bode plot. Okay? The pole, 1K, right, goes down to negative infinity, right? Makes sense with everybody, right? Because if I draw a mountain, right, here's my mountain, right? It's a pole, right? Everyone's seeing what I'm trying. See, I'm a visual learner, okay? I don't like numbers. I like drawing pretty pictures, okay? Pole, right? 10K, 100 hertz. Does that make sense? What's the value right here? With this being 20 dB per decade. The slope, right? What's the value there? Minus 20 dB. Is that good with everybody? Now let's go back to my phase thing, okay? The easiest cheat code, if that right there is my pole, right, is that at that pole, my phase, going back to my helper right here, okay? You have positive phase here and you have negative phase there, okay? This right here is going to give you some type of degrees. If you convert, what's 1 in terms of degrees? 1 angle 0, right? And if I add a phase right here, it's going to add degrees, correct? And then this one is going to subtract degrees. Is that making sense? Let me just verify with the website. Let me see. Where's my phase? There we go. There you go. This is what I was talking about. Give me a second. Take a picture. See, this right here is your 0, okay? This right here is your phase. Is that making sense? Am I teaching this right now? Anyways, you see that right there? This is your, what's omega naught or omega 0? Resonant frequency, your knee frequency, your reference frequency. So this is our reference, right? This is the pole, right? Or, yeah, the pole, right? So the phase, let me just go back again. Minus 45, okay? Right? Minus 45 degrees. I'm going to put that right there, okay? Right? Then I'm going to go up like this. Draw that big circle. Draw this big circle, okay? Right? This is what you're going to do. The slope of this is going to be minus 45 degrees per decade, but it stops, well, at here, okay? Minus 90 degrees, and then here's 0, okay? One pole gives you, what do you call it? Let me see, 90 degrees range. Okay, does that make sense? So when you see a pole right here, put your first dot right there. That's your minus 45, and then you have to go 45 down and 45 up, and then you got that total 90-degree phase shift. Okay, is that making sense? All right, when you do your little signals and frequency responses. All right, so this is page 7. There we go. Can't draw today, y'all. And then I think I'll demonstrate what I want to show you guys, okay? 0, Bode Plot, right? So repeat after me. Draw, right? This is my frequencies, okay? And a 0 needs to look like, if I tilt it like this, so if I do 1K right here, right? Looks like that hole, right? Right? If I flip this paper like this, you see that 0, that hole, right? Is that making sense of it? This is how I'm remembering Bode plots, all right? And I'm going to go 100 ohms or 100 frequency hertz, 10K, right? Is that making sense of everybody? This right here is 20 dB, right? And then the slope is 20 dB per decade, correct? Right? Now let me do my phase. Okay? So same thing with the pole, but for the 0, at this point, you can automatically put this as, draw that big circle right there, as 45, plus 45 degrees, right? Everyone understood? And then I go up 1 decade, down 1 decade. Is that cool with everybody? And then it goes like this. Okay? And then this guy right here is going to be your plus 90 degrees. And then this guy right here is your plus 0 degrees. Okay? Is that making sense with everybody? With a plus 45 degree per decade slope. All right? Everyone following that? Making sense? Actually, let me show you something funny. Let me see. 420. Let me see. You guys like all my classes? Electronics 1. Go back to my fall. Let me see if I showed this to my previous students. Lab 4. Is this correct? No, this is the wrong one. Let me see. Lab 3. No. Where is Lab 2? No, wrong one. This is what happens when I have a lot of things. No, wrong one, long one, Thought I had a frequency response lab. Give me a second. It's probably my 221. Let me show you this. There we go. Who remembers 221? Oh, not that one. Lab 2. Where is my frequency response lab? Thought I had it. Arrgh. Oh, here it is. Is this it? Yeah. See, this is what I wanted to edit. Electronics 1. This is what I wanted to publish for you guys. But let me see. I don't think I showed this. Yeah, where's my drawings? Gosh. Anyways, I'll find it somewhere. Everyone understanding what's going on with this? Okay. So let me go to the final thing that I was going to give you guys. This is the answer. So who remembers that one equation? V out is equal to V in 1 over, is anyone bothered if I do this? 1 plus J 2 pi FRC, right? Everyone good with that? What if I do this? 1 over 1 plus J F over F3 dB. Anyone bothered by that? Or everyone confused? F3 dB, where, what do you call it? F3 dB, right, is equal to 1 over 2 pi RC. Is that making sense with everybody? And then what's R and what's C? Right? The resistor value and the capacitor value, 1K and 1 and I don't know, 10 micro. Is that cool with everybody? Anyways, what happens if F equals F3 dB? So V out F is equal to F3 dB, right? What happens if they're both equal? 1 plus J F3 dB over F3 dB. What's that equal to? Right? Is that making sense with everybody? And then what happens if I do the magnitude of V out over V in? Right? What's the magnitude of 1? 1? What's the magnitude of 1 plus J? Square root of 1 plus square root of 1, right? Right? That making sense with everybody? What's this equal to? Is anyone triggered by this number? Has anyone seen this? 707? Yes? Yes? You have seen it? Okay, good. We're still teaching things. Or 707 is LOL upside down if you flip it around. Anyways, what's the what do you call it? 20 log 10 .707. Right? Actually, it's minus 3 dB. Right? I think so. Yeah, I'm not trusting myself. MATLAB. Okay? So, we want to have this kind of condition, okay? This is a singular pole. Let me just wait till MATLAB starts complaining. You guys like MATLAB? Or no? It's okay. You can tell me the truth. If you say you like Python, that's fine. Anyways. We have this very simple little number right here. That's a simple pole, right? Your knee frequency. Let's see if I can draw this right here. Right? This right here is going to be your pole. And why is it a pole? Because it's at the bottom, right? Numerator is a 0. Denominators are poles, right? What makes this thing go to infinity? If f goes to infinity, then this thing goes to 0, right? 1 divided by 0 is infinity. Pole. Okay? Everyone understand? Now let me just do the... Oh, this is from my last lecture at Signals and Systems. Let me see. Yes, you can use this as a calculator. 20 times log 10, what do you call it? 0.707. Am I wrong? Minus 3 or minus 3 dB? I just needed a sanity check. I'm having an off day today anyways. Everyone cool with that? Right? And then if I were to do the other case, which was, what page is this? This is page 8. Okay. Whew, you guys are getting education's worth, okay? Let's just say I have this kind of condition where I have V out is equal to V in 1 plus J, let me see, J F over F3dBz, right? Right? Is that cool with everybody? So then what's the what do you call it? The condition. So if f goes to infinity, correct? Right? That means this whole thing goes to, well, infinity, but it's a value that just goes to infinity. That's how I want to say it. Well, if this value, this f goes to 0, then this whole term goes to 0. Does that make sense? Right? Everyone following that? Yes? No? Maybe? Because what I was trying to do was like this. What do you call it? 20 log V out over V in is equal to, what do you call it? Let's ignore that. Square root of 2. Right? Everyone understanding what's going on? Right? I'm trying to do that 3 dB condition again. Yes? No? Maybe? Okay. Anyways. Because what I'm trying to get to you guys is if you wanted to draw like a numerator over denominator, and you have, what do you call it? What's that one trick in terms of S? S plus A, S plus B, S plus C, S plus D. Right? Right? Laplace transforms. You can create any function by poles and zeros. All right? This is a, what do you call it? Intro to control system theory, okay? Or DSP, all right? So yes, basically this is not worthless. You guys can use this a lot in your future classes, okay? So that's what I'm trying to get to you, okay? So that ends that. Now let's go back to what I'm trying to show you. Actually, should I go to my live demonstration? See, Camlink. You guys like that? You guys see that? Anyways, let me show you the fun parts. So this right here is a function generator. And this is what I want to end the class with, okay? An active lab showing you guys that your education is worth a lot, okay? So maybe I should have had Shockable, what do you call it, design the circuits. Okay, this is 1 micron, right?
Yeah.
And let's do 1 micron. 1 micro, okay? And then where's our 1K resistor? Or oh, that's where you place them.
Okay. And that for exactly 1.2 and 8. 800. This is 800.
Which one?
Wait, 800 to 1.
This is 100?
800.
800 ohms?
Yeah.
That's fine.
This is 1.2.
1.2? Let's use the 1.2. Okay? So let me show you what I'm trying to do. Okay? You guys like these breadboards? See. Hey, you guys like these quality? This is my 4K Ultra camera. Let's just say I have a 4K camera for personal reasons, not the reasons you guys are thinking of. So yeah, let me see. Dang, this is cool. You guys wish you got this education? So that right there is a 1.2 kilo ohm resistor, right? And a capacitor, right? And then you got the minus part of the capacitor. And then what I'm going to try and show you guys, let me see. Let me grab 2 probes because I should have prepared this a lot sooner. And yeah. Maybe I'll make my announcement because I need everyone to keep my labs clean. Okay. There we go. Nice. Okay. So if you guys haven't noticed, I have organized the cabinet, but I think a lot of my 221 students made a big mess. But because I finally got color code things. Let me show you. You see those colors? I put those in there, I think during spring break. See? I sorted them by color because, you know, I have OCPD. I want to make sure I know what I'm doing. Right? You guys see that right there? The colors? Right? See? I'm making these labs nice, okay? So I'm going to punch this yellow cable into the, let me see. There you go. Guys like that? Getting your education's worth. Okay, punch this yellow cable into the yellow port. Okay, I'm gonna punch this purple cable into the blue port because they're kind of similar. And then I'm gonna grab this one. This yellow one's gonna be VN. All right, and don't forget to make sure you set this to times 10. And why? When you add, what do you call it? You add this resistance, right? Times 10 it. Okay, it gets rid of that weird noise. So basically this is a filter, okay? It tries to get rid of all that high frequency noise. It sucks it up, okay? And then what am I gonna do with channel 1? Right, if I double click there. Let me see if I can decrease the contrast. I don't think I can. Well, let me see, Q. Let me see, auto white balance, let me see if I can do this. White, black. Let me see. Daylight. And let's see. We'll play with this later. Anyways, I'm gonna plug this into VN, which is our resistor right here, right? So I'm gonna probe this right here. Oh, there we go. And then what am I gonna do with this guy? I'm gonna ground it. Okay. Go. Cool. Everyone getting their education's worth now? You wish Dr. Zai taught like this? Hey, who said he didn't teach? I'm playing, no. Please, Dr. Zai, don't fire me or whatever. I'm going to put the purple cable right here to the output, right? Right? And then honestly, you can prepare me another breadboard with like a low pass and a high pass filter, okay? Any configuration, right? Is everyone seeing that? Okay. So now, what's this cable called right here? Or I don't know what's the street name? It's the function generator cable, right? It's a BNC to what do you call it? The hooks, right? You guys seen that? Always use this cable, okay, on the function generator. Not here, okay? Don't put this in here. You're gonna burn this. Funny enough, you see this right here? Or actually, let me see if I can tilt this guy down a little bit. There you go. Is that better? A little slanted. Give me a second. Is this more than what Doctor's Eye does? There you go. Man, I love this. This is great. Okay. This is the arbitrary function generator. I'm going to punch this in right here. Okay. And now what I'm going to do is I'm going to connect this to my circuit. I'll get rid of all these components, or maybe I'll use them. I don't know. I'll think about it. Okay. I'm going to put this right here is my V in, right? Red is V in. This is ground. Is that cool with everybody? So I'm going to put V in to this resistor right here, right? Everybody see that resistor? Boom. Then I'm going to ground my capacitor like this. Boom. Come on, there you go. Is that cool with everybody? Little mess, maybe a little better. It's okay. Anyways, what I'm going to do is, well, I should have done this by hand. It's okay. I'll show you guys a cheat answer because I want to get stuff done. Okay? So there's this button right here called arbitrary function generator. Let me see if I can get the focus. Come on, focus. It's okay. I'm going to press on this guy right here, or arbitrary function generator. Yeah, you guys won't see this at all in your other ones. Utility. Let me see. Input output. Let me see. Let me remember. Measure. There we go. Because I want to measure a frequency response. Is that correct? Okay. I wish you guys can see this. Wait. Let me see if I can. My filter works. Can you see that? Is that a lot better? Anyways, time or no? FRA. Frequency response analysis, right? We're going to get a Bode plot, okay? So what's my input source? Channel 1, let me just turn on the lights. Channel 1, right? The yellow cable. And then I have this purple cable right here, right? That's my output. So input, output, right? Add. Okay, now it does its thing. Okay. Now let me see if I can darken this. Cool. And then I'm gonna click on this. Let me get rid of this. You guys know how to get rid of things? Delete measure, delete measurement. Okay. Power 1. Input, right? Internal generator. And my amplitude is 100 millivolts. Not that bad because 100 millivolts divided by 100 millivolts is 1, right? dB is 0, right? Cool. So I'm gonna preset. Presetting just says, hey, prepare for test. Okay? And now I'm gonna do the following. Okay? I'm gonna press this button right here, the run and stop. Let it roll. Maybe I should have set the frequencies. Look, you see it's doing things now. What frequency is that? 126 hertz. You see this number right here? I don't know if you guys can see it. 159, 201, right? We're at 255 hertz, correct? And you see how these waves are kind of dancing around, right? 407 hertz. That making sense to everybody? So this is honestly what I would have done with the lab today, was to bring this instrument to every table, and it's gonna get your Bode plot in like 2 minutes. And then all you do is just eat your cookies, sit back, relax. This is real engineering, okay? Because what do we do in the real world? We use calculators, we use Python, we use tools, LT Spice, and then we show around, go outside, enjoy life. Is that cool? Not that hard heavy math or ChatGPT quizzes that you guys are doing. Or I don't know. If I were to give you guys a quiz, you know what my quiz would be? Draw me a Bode plot of a 1K resistor and a 10 micron capacitor. Does that sound like a fair quiz? Literally everything I talk about. I'm not a hard professor. I really don't. Just show me your work. Okay, don't draw the answer. Be like, I memorized the answer. Because you know what I'm gonna do? I'm just gonna change the resistor to 2K and maybe the capacitor to 100 nano. Can you do the same thing? And then worse yet, if I did a high pass filter, I just add that or with the two. I'd go over it in class. Okay, I don't want to show you guys something you guys aren't capable of, or you guys are, but I want to make sure everyone has that equal chance. Okay, I know a few of you guys are like, this is boring, which is okay. If it's boring, it's fine. Okay, but for those who are really like not understanding, I'm thinking of you guys too. Okay, so I'm trying to capture everybody. Those who are excelling in my labs, finish the lab, go home. Okay, and for those who are struggling, come see me. All right, I'm always happy to help you guys. So let's see, did it finish? No, not yet. But yeah, you see how, let me see. You see this green line right there? That's your gain. That's your Bode plot. And that's your phase right there. Something's wrong, but I'll check that in a second. Why is that at 20 dB? I don't like this. Yeah, I don't like that top one right there. You see this range right here? This right here doesn't make any sense to me. That right there. Okay, I like this, whatever this guy is. I should have started there. Oh, look, you see? And then you see how it starts coming back again? And it comes up, yeah, it comes up again. You see right there? Let me zoom into it. Oh, if I zoom in, that's a lot better. Oh yeah. Okay, let me just move this up. Okay, come on. Do you guys like having a crazy lab director like me? Oh. There you go. Wrong one. Whoops, I would have broken my camera. Sorry for the headaches, y'all. There you go. Okay. So can everyone explain what's going on? Just get back here. You guys see this right here? Right? Ignoring this, okay? This is 0 dB right here, right? Let me just move this a little bit. There, right? You see that 0 dB, right? Does that make sense? You see that 0 dB? I don't know what the heck was going on here. I really don't. 10K. And that's probably some residue. But yeah, this right here, where's the pole? I don't know. It's somewhere right here, right? Like 200 or 300 kilohertz, right? We have, okay, let me just write something, okay? Let's change this camera. Because maybe we should start pre-calculating things before we go crazy. Okay? Come on, Mr. Camera. Come on. Hello? IPVO? Wait, wrong one. Ugh. So here's the condition, y'all. Hey Shakibul, what? So you said that was 1.2K?
Yeah.
And then that capacitor, what's the value?
1 micron.
1 micron?
Yeah.
Okay, we're gonna do an investigation, right? What do you call it? This is how you learn as an engineer. 3 dB. F 3 dB, right, was equal to 1 over 2 pi RC, right? 1 over 2 pi 1.2k times 1u, right? What's that equal to? Aha. So 1.2 E3, right? What's E3? Not that gaming convention. E3 is 10 to the third, right? 1,000 kilo, right? Times, okay, let me write that. 12, 1.2, 1,200 ohms, right? 1.2 E3, right? Times 1 E minus 6, right? 1 micron, right? And then times, 2 times pi times, actually, no. 1 divided by 2 times pi times 1.2 E3 times 1 E negative 6. 132 hertz. Is that correct, gang? Is that correct? Let me see. Boom. Select camera. Boom. Cam link. Because that means it would be up here. So something's wrong. Okay, this is the 0, right? This is a pole. This is another 0. Something else is going on. Let me check. So funny enough, this part right here is actually correct. But why is it up there? Let me just check the settings, okay? Oh, is it because it's touching tips? The heck? Anyways. Whoa. Okay, something's wrong. Okay, there we go. I'm going to do this again. Points per decade, I'm going to start at 100 hertz. Or actually, let me just start at... Oh, come on. 10 hertz, right? Enter. And I'm going to go to... what did I say, 100K? Let's go to 10K, okay? 10 kilohertz. Enter. Amplitude. What's my max amplitude? Can I do 1 volt? One, what do you call it? None? Enter. Oh, I can do 1 volt. Great. High Z. That's probably what I did wrong. Give me a second, y'all. Oh. You know what I did wrong? I forgot to set times 10 on the other. Anyways. Preset. Now this should make a lot more sense, okay? Hey, lab director makes mistakes too. DC coupling. Then DC coupling. 10. Okay? Ready? Set. And yes, we're recording, so don't worry. That looks a lot better. I was wondering what was going on. Is that a lot better, y'all? So here's the other thing about this function generator, is that it does 3 samples before it averages them all out and draws a point, okay? So let's just say you and your friend are looking at a point. Well, you're probably going to say 1 volt, your friend's going to say 1.1, and then you have a third friend to confirm, oh, it was 1 volt. So that's what it's doing right here. It's measuring it 3 times, every single frequency, and then it's just jumping to the next frequency, okay? So you see how they're both the same? The yellow trace and the blue trace are the same, right? Because we're at the low frequencies, all right? Now that's better. You see how it's starting at 0 dB now? All right, if you guys don't see it. Right there. See? What's that red line right there? It's your phase. Is that cool? And then remember how we calculated it was at, what do you call it? What did I calculate? 100 and something hertz? Right? What did I say it was? Anyone type or write or listen? I don't know. What did I say? What does MATLAB say? 132 hertz, right? Let me go back to here. And then I think we'll end it right there, or right after it finishes this thing. So you see how it says 10 hertz right there, right? The thing is blocking the 100, but you see that dashed line right about... You guys see my mouse cursor, by the way? See that right there? That's the 100 hertz line, right? Everyone seeing that 100 hertz line in the middle of the screen right there? So somewhere between that and now you see starts skewing down. What does that mean? It's going down, right? It's the pole, right? The pole, or from your angle, here's the zero light. It's going down, right? The pole, right? It's going down, and then you see the phase is also going down too. And then you see, look at this bottom plot right there. It's measuring that for, like, I think it's measuring 50 cycles, about 50 cycles maybe, to get an average, like, what do you call it, phase and an average voltage value, okay? It's trying to make sure that's stable, okay? And then boom. So yeah, by the way, if you are doing your final project, I'll talk about that later next week, okay? And you need a really, really nice graph, or if you're doing research, or if you're doing something that needs like a filter response or a phase response, magnitude plot, let me know. I only have 2 of these machines. One of them's right here. The other one is in my bag somewhere over there. Okay, so I only have 2 of these very valuable equipment. I think it costs like $1,000 per license. I want to buy for all the labs, but you tell me. And I think we're done right there. Yeah, there it is. Let me just see if I can zoom in. Okay, so I'm gonna not auto scale. I'm gonna go from 17 hertz. Anyone bothered if I do this? 20 dB. Enter. And then this guy can be bottom scale is 40 dB. 40 minus, enter, and 0 dB. Does that look a lot better? You guys seen that phase? Right? Let me see if I can touch this. Why is it doing that? Auto scale. Anyways, is that pretty cool, y'all? And then let me show you one last thing before I end this class. Let me see. There's supposed to be a table. Are you kidding me? Oh, there it is. Okay. So if you use this machine, if you want to, let me know. If you have a USB stick, you can get the CSV.csv file and punch this into your MATLAB, your Excel, your Python, all right, and it gives you all the values, all right? And then here's a question. You see how it's going down, but it somehow goes up again? Why? And then you see the green line, it's somewhat going up again at 10K hertz. Why? That's a 0, right? There's a parasitic in the board. You start seeing stuff happen. Like, so someone's asking me, why am I getting weird results when I like change the frequency? And that's because there's some parasitics that we can't control. All right, that's where it starts becoming important. Are the cables looking good? Or anyways, you start valuing. Okay, if we're dealing with things that are under like 10K, right, 10 kilohertz, it's not too bad. But when you start going into the megahertz range, like little strays of parasitics can kill your board. All right, this breadboard right here can only operate, I think, up to like 100 kilohertz. So if you go anywhere above 100 kilohertz, this board starts acting like an antenna. All right, then it starts doing things you don't want it to do. All right, does that make sense with everybody? Did you guys get your education's worth today? Can you now do this at home or actually take this to your senior design or whatever other competitions or research work? So the point is, this is what's supposed to be the lab. Pretty chill, not that bad. All right? Is that a cool little lecture? All right, so I'm about to do, what time is it? What time does this lab close? 12:45? All right, I'm going to do a special second lecture. So if you guys want to leave, that's okay. But else, this is the end of the lab, all right? Lab 6. If I were to give you guys a quiz, I don't want to because he'll be like, what the heck? All right, I want you guys going home. Go enjoy the week, okay? Next week is going to be lab 8, right? That's going to be BJTs and then MOSFETs. But I'll be announcing your guys' final project soon, okay? I'm about to do another special second lecture, all right? Have a good day, everybody.